Assalamualaikum warahmatullah. You're most welcome for today's lesson. It's a continuation of yesterday's lesson where we're discussing the factors that affect reversible reactions. As a recap, we mentioned that we have four factors. Factor number one was a factor of temperature. Factor number two was a factor of pressure. Factor number three is concentration. And the factor number four is the effect of the catalyst. We discussed the first two factors, the effect of temperature and pressure. If you remember very well what we said about temperature, I said the temperature effect depends on whether the reaction is endothermic or exothermic. And we agree that for reactions that are exothermic, they are favored by application of a low temperature. And the reactions that are endothermic will require application of a high temperature. And for you to discuss this effect, you must be given the value of delta H. So here, delta H given is supposed to be negative, and the delta H here is supposed to be positive for you to use the temperature effect to discuss how it affects reversible reactions. And we concluded. On pressure, what do we agree? We say it is when the reaction is going to occur with volume increase or volume decrease. For example, sulfur dioxide plus oxygen gas reversibly is giving us sulfur trioxide from a balanced equation. We saw yesterday that in this reaction we have two volumes of sulfur dioxide are reacting with one volume of oxygen, and therefore is giving us two volumes of sulfur dioxide, trioxide. So what have we seen here? That there is a total of three volumes of reactants giving us two volumes of the products. And therefore we say volume has changed from 3 volumes to 2 volumes, indicating that we have increased pressure. So what did we conclude yesterday, ladies and gentlemen, our dear esteemed students? We say where there is volume decrease, what does it mean? The reaction requires high pressure. And where there is volume increase, it means the reaction requires low pressure. So, using this reaction that you see on a whiteboard, sulfur dioxide plus oxygen giving sulfur dioxide, what we notice? Volume is reducing from 3 volumes to 2 volumes. Therefore means when you increase the pressure, you favor the forward reaction. And when you reduce the pressure, you favor the backward reaction. So we discussed on this one and we concluded. And we ended by looking at reactions where there is no increase in volume or when there is no decrease in volume. Where volume remains constant, what did we agree? That if volume remains constant, then it means in such a reaction, the effect of pressure does not apply. And that is where we ended. So this morning, allow me look at the remaining 2 factors, and these 2 factors are the effect of concentration and the use of a catalyst. So let's venture into the 2 and we see what is going to happen thereafter. So let's look at the first factor. Find the factor here, the factor of concentration. How does concentration affect reversible reactions? I want to use a good example to advance my point home. I asked one student one time that what happens, imagine you are married, just my imagination. And somebody comes and takes your partner away and takes the partner for good. The student replied, I will replace. I said, okay, fine, that is good. What happens if in a room you are supposed to be having 10 students, they bring the 11th student and who says you are supposed to be 10 people in the room? I asked what happened. The student told me, what do I do? I remove one student because the room is supposed to carry how many? 10. And that was a wonderful expression and a wonderful answer. So for purposes of concentration, you can discuss the effect of concentration by noting that once an equilibrium has been established, so at equilibrium, concentration is supposed to be kept constant. Full stop. So if you change the concentration, if the concentration is changed by Roman 1 adding a reactant or adding a product, what will happen? The reaction will reorganize itself such that the added product or added reactant, let me follow the order, the added reactant or the added product is removed. If you add a reactant or product at equilibrium, the reactant or product you have added is removed. So that you go back to the original position. What happens in Roman 2? If you remove a reactant or you remove a product, what will happen? Here, they removed reactant or product is replaced. That is how concentration affects equilibrium reaction. When you add, the added is removed. When you remove, the removed is replaced. And that's how you can discuss the concentration effect. That's why that student say, if you remove the fiancé, he or she replaces, because you are replacing what has been removed. And when you add one from outside, the added is removed to keep the system constant at equilibrium, because you are not supposed to disturb the equilibrium once it has been attained. And that was a very good example and very good illustration. So let's look at any reaction which is equilibrium in nature. Let me look at a reaction between hydrogen and chlorine reversibly to give us hydrogen chloride, and therefore from the balance equation, that's the equation. So what we notice? That here, once an equilibrium has been attained, what did we say? The forward reaction is balanced by the backward reaction at equilibrium. None of the reactions is being favored here. So in the forward reaction and the backward reaction are equal, i.e. at F is equal to B. Forward is equal to backward reaction. We said the equilibrium has been established. So using the concentration effect, what will be the effect? Can you therefore tell me, mention, what will be the effect of adding? If we add, for example, hydrogen at this equilibrium point, what did we say? When you add at equilibrium, the added must be removed. When you remove at equilibrium, the removed must be replaced. And that is it. That's why sometimes in relationships, when one person walks away, the person is replaced for continuity and so on. So this is what's going to happen. So what happens once I add hydrogen? Have you seen I've added hydrogen? The equilibrium has established that I am bringing hydrogen from outside. So what do we say? When you add, the added must be removed. So what happens when I add hydrogen, dear students? So the notes are, the hydrogen added is removed by chlorine to form hydrogen chloride. So if I add hydrogen, this hydrogen that I've added from outside, I am adding this hydrogen and I'm adding, enter the system. So this chlorine say, my friend, even if they're not, I'm going to remove you. And once this reacts with this, what happens? They produce that. So what happens? When you add hydrogen, the amount of hydrogen chloride does what? Increases, because the added factor must be removed. So what happens if I add chlorine from outside? This added chlorine, I'm adding chlorine now. The added chlorine will be removed by hydrogen to form hydrogen chloride. So how can I favor the forward reaction now? I can favor the forward reaction by adding hydrogen or adding chlorine at equilibrium, because the rule says the factor added must be removed. So that is it. Now supposing I came back and said, this time I don't want to add, let me remove. With the same concept, I am going to remove. Let me remove hydrogen. So when you remove hydrogen, what happens? I come this equilibrium reaction and remove that hydrogen. The reaction says, oh, the hydrogen has been removed and must be replaced. So who is going to replace the hydrogen? This one. The hydrogen chloride decomposes to replace the hydrogen. So here, the moment I remove hydrogen, comma, we are saying the hydrogen removed is replaced by decomposition of hydrogen chloride. I.e., what happens now? Hydrogen chloride decomposes to give you hydrogen and chlorine. And therefore, what has been removed has been brought back. So this is what it means to remove. So in this aspect, what would happen if I kept this reaction and I remove the hydrogen chloride? So if I remove the hydrogen chloride, what happens? Hydrogen combines with the chlorine to replace the hydrogen chloride. So the forward reaction is favored. And therefore that summarizes what we said. When you remove a factor, the factor removed must be replaced. And when you add a factor, the factor added must be removed from the system at equilibrium, so that the concentrations do not change. I want to look at this question and equation on the chalkboard and see if you can, wherever you are, you can handle this question. I want to look at ammonia, formation of ammonia by the Haber process. So 2 moles, so nitrogen plus hydrogen gives us ammonia and establishes an equilibrium. From our balance equation for the reaction, this is what we have. So the question in the room is, I want you to think of an answer. State how the concentration of for example, concentration of Roman 1 ammonia can be increased. Roman 2, the concentration of ammonia can be reduced. Roman 3, this is A. B, I want you to still state how the concentration of hydrogen can be increased and can be decreased using the concentration factor. So what we notice here, I want to increase the amount of ammonia. How can I make amount of ammonia to go up, to continuously increase? I can be done by doing the following. Number one, you either add hydrogen. If not adding hydrogen, you can add nitrogen, because the rules say the added factor must be removed. So if I add nitrogen from outside, nitrogen added reacts with hydrogen to form ammonia. If I add hydrogen added will react with nitrogen to form ammonia. So in most cases, in all cases, the amount of ammonia is increasing. Number 3, how can I increase the amount of ammonia? By constantly removing. So I remove ammonia at regular time intervals. What do we say? The amount removed must be replaced. So if I remove this ammonia, the ammonia removed has to be replaced. So what happens? I'll be favoring the forward reaction. So there are 3 possible things you can do here. Number 1, you can add hydrogen, because hydrogen added must be removed to form more ammonia. Number 2, you can add nitrogen. The nitrogen added must be removed by hydrogen to form ammonia. Number 3, I can remove ammonia periodically. So each time you remove ammonia, it is going to be replaced. So how can I make the amount of ammonia to reduce? How do I reduce the amount of ammonia? I can reduce the amount of ammonia by, number 1, we can remove hydrogen. When you remove hydrogen, the hydrogen removed must be replaced. So ammonia decomposes. We can also go ahead and remove nitrogen. The nitrogen removed has to be replaced by the decomposition of ammonia. And lastly, what can you do? You can add ammonia at equilibrium. So when I bring more ammonia and add, the added ammonia must be removed because the equilibrium should not change. Because the equilibrium should not change, so the added ammonia will decompose to produce more nitrogen and hydrogen. As simple as that. So how can you be questioned to increase? How can the concentration of hydrogen be increased? How can I make the concentration of hydrogen to be increased? So we can increase the concentration of hydrogen by, number 1, you remove the hydrogen at regular intervals. If not, we shall also remove nitrogen. If not, what can we do? We can add ammonia. So when you add ammonia, you favor the backward reaction. Equally likely, you can now discuss how the amount of hydrogen can be reduced. So how do you reduce the amount of hydrogen here? It's the same effect here. So this is increased by removing. So whatever has been removed has to be replaced. So how do I reduce the amount of nitrogen? Amount of hydrogen. I can reduce the amount of hydrogen by adding hydrogen from outside. The hydrogen added is going to be removed. By adding nitrogen added must be removed. Or by constantly removing ammonia, removed ammonia must be replaced, and by doing so, you end up favoring the forward reaction. Now, if I forget about all of this, and I asked, without saying use concentration, state 2 ways by which the amount of ammonia can be increased. You can explain here the effect using only 2 possible mechanisms. Number one, you can use the effect of pressure because volumes can be obtained from a balanced equation. Number two, you can use the effect of concentration. We can't use temperature because there is no delta H that has been given. So my dear students, we use delta H temperature to explain if delta H has been given, enthalpy has been given. Since there is no enthalpy, we can now explain using number one, pressure. Because for pressure, we use a balanced equation and look at this as volumes. Or number two, we use the effect of concentration by either constantly removing one factor or adding one of the factors. And that is how the concentration effect is used to explain its effect on reversible reactions. We are now left with only one factor, which is the factor of a catalyst. So this was number 3. Number 4, the effect of a catalyst. What should we note here? That a catalyst has no effect, but only increases the rate at which the reaction takes place. Full stop, i.e., a catalyst favors both the forward and the backward reaction. Equally, it favors both the forward and the backward reaction equally. Therefore, what does it mean to all of us? That we have majorly 3 factors that we can talk about that can be asked. Number 1, temperature. You must be given delta H. Number 2, pressure. You must obtain from the balanced equation. And number 3, the effect of concentration. Because the catalyst has no effect on the equilibrium. It favors both forward and backward reactions simultaneously. I now want to remind you about the objectives. 1, what is a reversible reaction? Number 2, state the factors. Number 3, how are the factors going to be affecting the reversible reaction? Explain. And I think the objectives that were stated can be achieved and have been achieved at this level. So number 1, temperature, we finished. You must have delta H. Number 2, pressure. Use a balanced equation to declare whether the volume reduces or volume increases. And conclude. Concentration, what you need to remember, when you remove a component at equilibrium, you replace it. When you add a component at equilibrium, you remove it. And I think those are dynamics of the ecosystem by the biologically. And so when you add, you remove. When you remove, you replace. That is how the concentration affects reversible reactions. And with the catalyst, what happens? It has no effect, but favors both backward and forward reaction. And therefore, for it, you can just be asked, what's the effect of the catalyst? It has no effect on equilibrium reactions. Having said so, it is therefore necessary that we look at the applications of reversible reactions as our last subtopic in this topic. Applications of reversible reactions. So application number 1, we use reversible reactions in the Haber process. So use it in Haber process. And I want to quote. The equation say nitrogen, a gas, plus 3 moles of hydrogen, a gas, reversibly, the arrows are the same size, same length, meaning forward is equal to backward will give us 2 moles of ammonia, which is a gas, and our delta H given was minus 94 kilojoules per mole. So what did we agree in summary? We say this reaction is going to be favored by, the forward reaction is going to be favored by, and I want to summarize that the reaction is favored by, number 1, application of low temperature. Low temperature. Why low temperature? It is because the reaction is exothermic, if you remember very well, minus 94. So we shall use a low temperature. What else? Let's look at the volumes. This reaction is favored by application of high pressure. Why high pressure? Because 1 volume plus 3 volumes gives us 4 volumes of reactants, but we are getting only 2 volumes of the products. So high pressure because the reaction is by volume reduction from 4 volumes to only 2 volumes. So we are going to use high pressure. But ladies and gentlemen, high pressure is very difficult to provide. High temperature is extremely very difficult also to provide, expensive. So when you are discussing preparation of nitric acid by Haber process, what were you told? What did you write down in your notes? You wrote down in your notes that the reaction proceeds at a certain temperature and at a certain pressure, if you recall very well, because from our information we are gathering that here we need a low temperature. But at low temperatures, reactions are very slow. And yet we need a lot of ammonia at a go to make as much acid as possible. So what happens if the reaction is going to be very low? You come up with an alternative. How do you improve it? And therefore, if you remember in your notes, what did you agree? At industrial level, therefore, during the Haber process, a compromising temperature, a suitable temperature of 450 degrees Celsius is used. 450 degrees Celsius is used, and during the Haber process, a suitable pressure of about 250 atmospheres, if you recall very well, to around the 400 atmospheres is used. Ladies and gentlemen, in an ordinary lab, 450 is a very high temperature, but in an industry, 450 is a very small temperature, because industry give out heat in terms of thousands and so on. So 450 is appropriate enough for the reaction to be very fast and at the same time give us as much ammonia as possible, so this ammonia can be used to manufacture nitric acid. So this is one of the applications of reversible reactions. I want to repeat that as a reversible reaction is formation of ammonia during the Haber process favored by use of a low temperature, because the forward reaction is exothermic. It is favored by application of high pressure because volumes are reducing from 4 volumes, 1 plus 3, to 2 volumes. But low temperature, reaction in most cases are slow. High pressure is difficult to provide. Therefore, a suitable temperature of 450 degrees and a pressure of 250 to 400 atmospheres is used, where the reaction becomes fast enough and the amount of ammonia being formed is large enough to be used in the manufacture of nitric acid. So, when you check your work, what happens? Describe how nitric acid is formed, prepared, manufactured in the lab on a large scale. Hey, it is formed from ammonia, by catalytic oxidation of ammonia. Ammonia is formed by Haber process, where 1 mole of nitrogen reacts with 3 moles of hydrogen to form ammonia at a temperature of 450 degrees and a pressure of about 300 atmospheres. In the presence of a catalyst, which catalyst that? Iron. So the purpose of iron as a catalyst is to make the reaction move faster, but has no effect on the equilibrium position. But we are choosing a temperature of 450 and a pressure of about 300, which is good enough. And therefore, when you ask to explain how nitric acid is formed from ammonia, we need this information to be captured. Yes. Right? For students who have had a chance to look at one of the more papers done by Jeb and so on, this is one of the questions and so on. So that is application number 1. So let's look at application number 2. I hope you have captured this one here. Application number 2. In application number 2, I'm going to look at the contact process as application number 2. So I'm removing this reaction and I'm replacing it with contact process used in the contact process. What's the contact process? It's a process that leads to manufacture of sulfuric acid from sulfur dioxide. So I am changing the equation from nitrogen and ammonia being formed to sulfur dioxide being formed. So in the contact process as the second application, sulfur dioxide, a gas, reacts with oxygen, a gas, reversibly, and we obtain sulfur trioxide, a gas. And from a balanced equation, that's what we have. Since we have 2 sulfurs here and we have 1 sulfur, also multiply this by 2. So what we notice? The enthalpy of formation from the one that I gave you is delta H is equal to minus 93 kilojoules per mole. Therefore, from the knowledge of reversible reaction, the factors, what we notice? This reaction is going to be favored by, again, low temperature. Why is it a low temperature? Low temperature because the foil reaction is exothermic. This reaction is going to be favored by application of high pressure. Why high pressure? We are changing volumes from 3 volumes to again 2 volumes. This time there are not 4. This time there are 3 volumes. Change to 2 volumes. And because there are 3, change 2 volumes, volume has reduced. Therefore, high pressure is used. But at industrial level, at low temperatures, reactions are very slow. And very high pressure is difficult to provide. Therefore, what happens in this particular aspect? Again, a compromising temperature of 450 degrees Celsius is preferably used where the reaction is fast enough. And an appropriate pressure of about the same atmospheres is used. Some books quote 2 to 3, others quote the same 250 to 400. So a same pressure is supposed to be a high pressure of about 250 is not very high enough, and therefore we choose that as the appropriate conditions at which the reaction takes place. So one, I want you to remember that we apply reversible reactions in contact process and in Haber process, and when you are asked about describe how sulfuric acid is manufactured by the contact process, this temperature is needed and the pressure must be quoted when you are answering or when you are writing your essay, because we look at them as compromising temperature. And the notes, what are you given? That an optimum temperature, a suitable temperature, a compromising temperature, and the pressure of. You must quote the values, and after quoting the values, what happens? They become mapping points. So which catalyst do we use here? We use vanadium 5 oxide. We are using vanadium 5 oxide as a catalyst so that the reaction becomes fast enough, but does not change the quantities. Favors both backwards and forward reaction. So, but the major issue is we attain the equilibrium position much more earlier than expected. So I want to end the work on reversible reactions by reminding my classroom again that number one, I need to know the definition of a reversible reaction. How do you define a reversible reaction? A reaction in which there is both a forward and backward reaction taking place simultaneously. A reaction where reactants form products and products form reactants simultaneously until an equilibrium is established. Examples of reversible reactions. We have seen contact reaction, Haber reaction, heating ammonium chloride, oxidation of nitrogen to form nitrogen dioxide, also to form nitrogen monoxide in the lab, hydrogenation of iodine, and so on as examples. Factors. Majorly 4 factors: temperature, pressure, concentration, effect of catalyst. We have explained each of those factors, and the applications are as seen on the whiteboard, applied in the contact process and applied in the Haber process. It is time for you to answer 1 or 2 questions as your assignment and as a review before we get set for another topic that's going to come in the nearby future. Alright, so we shall write the following questions down because I want you to try as much as possible to answer the following questions. So I'm giving an assessment work. So this is self-evaluation work. Self-evaluation stroke assessment. It's like a test now. Having covered what we want. A. Define the term reversible reaction. B. Give 2 examples of reactions. Full stop. In each case, write an equation. In each case, write an equation to illustrate your answer. Part C. A student, Sendagala, is asking that I have a question. In the contact process at industrial level, heat is provided to the process. Is heat provided at industrial level? That at industrial level, heat is provided. He's asked whether heat is also provided. Now, the provision of heat we want to say, at industrial level we say, you have to look at the reaction. The reaction has delta H. Before you get back to the question, we say for contact process, the heat that is given out is 93 kilojoules, kilojoules per mole. And therefore it means that this reaction should have taken place at a very low temperature, supposed to have been normal room temperature. So a room temperature means that this reaction should have taken place at about 25 to 30 degrees Celsius. But at 35 to 20 degrees Celsius, the reaction is not very fast enough at industrial level. And therefore, the temperature is changing from this to about 450 degrees Celsius. And honestly speaking, when you look at industries, temperatures in the industry are extremely very high temperatures. They go to thousands and thousands. So remember, during contact process, during the harbor process, if you look at industrial level, the industrial temperature is supposed to be about 17,000 degrees Celsius. Now, when you look at the 450 versus 17,000 degrees Celsius, what does it mean? Honestly speaking, at an industry, this is a very small temperature compared to what it's supposed to be. So we are saying at industrial level, 450 is a very low temperature because the temperature is supposed to be about 17,000 degrees Celsius. Blast furnace reactions, smelting, very hot air, extremely very hot. So 450 becomes a small temperature. So don't look at 400 and say the temperature is very high. At industrial level, 450 is a very small temperature. It is a very small temperature at industrial level. So let's write the questions and finish first, then from there shall continue. So, state 3 factors that affect equilibrium reactions. Number two, consider a reaction between hydrogen and nitrogen. To form ammonia. Full stop. A. Write equation leading to formation of ammonia. B. State and explain how formation of ammonia can be favored. State and explain how formation of ammonia can be favored. And C, give Give, one application of reversible reactions or processes. Yeah, there are two questions here, one from Musuga and the other from Fatuma. The other one is from Kalik, because I just say where the classroom is right. I am supposed to know the delta H of every reaction by head. Please do not cram those values of delta H. If they want you to use the data, it is given. If merely the atomic numbers of the first 5 elements, the periodic table, you don't cram them, then why do you cram the values? Don't. If you want to use them, they are always provided. For you is, once given, find out is it positive or negative value, then from there you can use it. Please don't cram the values. The question paper will always provide. And if they have not been provided in this particular topic, then it means you cannot use delta H to answer the question. Use other factors to answer the question, and so on. Fatuma says, is there a specific what? Delta H for each reaction? There is what we call from the book of data. There is a book of numerical data that we use. But even if you Google on internet, you can get those values. But if they are supposed to be used, the examination paper gives. So please, don't bother yourselves with those values. You leave them. If wanted, they will always be given. There is a book of data, it has all those values. That's where we pick them from. And when you Google after the lesson, you will get those values. But for examination purposes, revision purposes, don't cram them. Sometimes we don't even give what? The values. We just give signs. Alright. Now, the first question is okay. 2 examples of reversible reactions. You are at liberty to choose any out of the 4. Out of the 4, you cannot choose from 3. You can choose from temperature, you can choose concentration, you can choose pressure. Why can't you choose a catalyst? What did we agree? A catalyst has no what? No effect. So that one you can leave. So I want 3 factors, and therefore those are the 3 factors you are supposed to be quoting. Here, quoting a catalyst, you don't get a marker because we say it has no effect. Consider this reaction. Write the equation is okay. State and explain how formation of ammonia can be favored. Now here, which factor can you use? Can you use the factor of temperature? Definitely no. Why? Because there is no information on delta H. So in this particular question here, the second equation, when they say state and explain the factor that can affect formation of ammonia, what can you use? You can only use pressure, because pressure you get the information from balanced what? Equation, and you can use the effect of concentration. But for all these 2, pressure is the best factor to use because you're going to get it from the balanced equation of reaction. And from concentration effect, you either add or remove. We say when you add, the added is removed. When you remove, the removed is replaced. So you can discuss about that one. That's what we refer to as when I talk about question what? Interpretation. Now look at the content, pick out what is good and use to answer a question and leave what you want to use to answer a question. Now, they are saying, state and explain how formation of ammonia can be favored. Now, can we use a catalyst here? You can't use a catalyst. So you can only explain formation of ammonia by using pressure effect and concentration effect. Part C, give one application. How many applications do we write in class? Or have we written today? We say, first application is Haber process, formation of ammonia. Number 2, contact process. Out of these 2, when you say Haber process and application, you are wrong. Is there anybody who can think of why that answer is wrong? Why is the Haber process wrong now? I want only 1, and we gave 2. Now when you use Haber process, it becomes wrong. What makes the Haber process to be wrong now? Not a correct answer in this question, because the question is already talking about the Haber process. So because the Haber process is the one being investigated, number 2, you are left with only 1 application left. So which application is that? It is only the contact process that you can give. So there is only one answer here. So in marking, I would have said accept contact process, reject Haber process. But if you give us Haber process, now I'm rejecting. I'm rejecting Haber process because the question itself is about Haber process. So you cannot again ask its application, yet the one being investigated because you are in the Haber process. So this is one of the questions. Here we don't have delta H. Unless I say, consider a reaction between hydrogen and nitrogen to form ammonia, and the reaction is exothermic. There I have given a guideline without mentioning how much energy is being used. You can use the delta effect to talk about it. So, my dear students, don't strain yourselves with values of H either being positive or negative. It's supposed to be used. The information is found in the question. So if there are challenges to this question, then it means there is something we missed out. I'm here to investigate, I'm here to ask the people behind the machines to find out, is there a possibility of you answering these questions and forward them so that we can download them, we can mark them and return the effects back to you, because it is possible. You can do the work, you send the work, we mark it on the computer to assess ourselves, and then after send back the work, we feed it back to you. And I know that is very possible, because using Google Classroom and so on, this information can be answered. You send it, we mark it, and find out how best you have achieved. And I think that is something that you have to venture into and give a feedback. Now next what? Now next discussion. We are waiting for other questions to come from your side. If they are there, you are free to send more questions so that we can respond them, because we have finally concluded on reversible reactions and rates of reactions. So what's going to follow next? Totally different new topic completely, either thermochemistry or electrolysis. So if there are any other questions, you are free to forward them. And I think the time that we are supposed to be having for reversible reactions and rates is this. So this evaluation exercise, we shall be glad if you handle those questions and find a way of sending them. You can send them as a WhatsApp, I think. You have a WhatsApp group for the school, yes, that we are using. Answer those questions and say, take a picture of your work. Take a picture using cam scanner, using all the mechanisms you know, and forward on our WhatsApp group so that I can look at the questions, look at the responses, and plan for regulations if there is any. I want to thank you so much for attending today's lesson. The struggle continues. Remember, as stated, Kibuli, the only school, we must be different from others. Assalamu alaikum wa rahmatullahi wa barakatuh as we prepare for our next lesson. Thank you so much. God bless all of you. As stated, Kibuli, the only school, we must be different from others. Assalamu alaikum wa rahmatullahi wa barakatuh as we prepare for our next lesson. Thank you so much. God bless all of you. As stated,